Okay, hello. This is the next video. This is the fourth video on linear transformations. There's a lot to say about linear transformations when it comes to linear algebra. And the topic of this video is about where do linear maps or linear transformations, they're the same thing, where do they send lines and planes? So we know that when you have a linear transformation, it will take points in Rn to points in Rm if you have an n by n matrix. And where do these matrices send entire lines and planes? So let's just review how to describe So first we're going to talk about lines. How do you describe the line through two given points, through P and Q? So for instance, let's say that you're in R2, okay. You're in R2, and you have this point P, and you have this point Q, and you have the line through P and Q. How do you describe the points on this line? Well, you have the origin. And the way to do it, so this is the parametric equation describing a line. So first you take the vector from the origin to P. Let's call that V. And you also have the vector from the origin to Q. Let's call that W. So it turns out that all the vectors along this line, all the points on this line can be described in terms of V and W. And how do you do that? Well, if you take this vector, W minus V, okay, that's the vector from P to Q. Now all the points on this line are parallel to W minus, well, no, I should say that this line is parallel to W minus V. That's the correct way of saying it. The line is parallel to W minus V, this vector. And the idea is, if you look at the equation R of t equals V plus t times W minus V, okay, what does that look like? Well, if you plug in 0, you get V plus 0 times W minus V, and then that's just equal to V. So you know that if you plug in 0 into this function, you get V. So in other words, you get this point. You're here at t equals 0. Now what happens if you plug in 1 into this equation? If you plug in 1, you get V plus 1 times W minus V, and that's V plus W minus V. The V's cancel and you get W. So when t is 1, you are here at Q. And what happens when t is between 0 and 1? Well, between 0 and 1, you're going along V. So let's say that t is a half. So what this is saying is that you have V and then you take half of W minus V. Well, if you do that, you're just going to go along halfway along W minus V, starting at V. So you're going to be at the point V, and then you take half of W minus V, and so you're here when t is at 1/2. And so on. So if you take t to be negative, you're gonna end up at these points of the line, and if you take t bigger than 1, you're gonna be at the points past Q. Okay, so this is a parametric equation This is an equation for the line through P and Q. Another way of writing this is you can just distribute the t across. So you're going to get R of t equals 1 minus t v plus t w. That's another way of writing it. Okay, you can check that just by distributing that you get the same thing. So this is a nice way of putting it, because you see that if you plug in t equals 0, you get v, and if you plug in t equals 1, you get w. If you plug in anything else, then you're going to get a different point on the line. Okay. So if you plug in all the values of t into this function, then you're going to get this line that goes through P and Q. So what happens if you want the line segment? So you don't want the entire line. So this would be the line segment from P to Q. Well, if you wanted that, you would just want a piece of the line, and you only want a piece from which values of t? It would just be the values of t from 0 to 1. Okay, because anything less than 0, if you have something less than 0, if you plug in a t value that's less than 0, you're going to be on this part of the line. And if you plug in a value of t that's bigger than 1, you're going to be in that part of the line. If you want to be just between P and Q, those are going to correspond to the points where t is between 0 and 1. And so what you would say is you have the same R of t. It's 1 minus t v plus t w, but you have to restrict t to be between 0 and 1. Okay, so that would be the line segment from P to Q. By the way, we can play around with this, so let's just do some examples. So what if you want, this is just an aside, what if you want Q at t equals 0. So if you think of t as time, you want to start at Q, and you want P at time t equals 1. Then what would you do? Well, then in this case, you would, so to start at Q, you would start at W, so it would be W plus 1 minus T, it would be W plus TV, right? W plus TV. Not TV. Let's see. V minus W. Is that right? When you plug in 0, you get W. When you plug in 1, you get V, right? And then this is also the same as 1 minus T W plus TV. So that's how you would do it if you wanted to start at Q and end up at P when T is 1. Now what if, another thing you can do, you can adjust T. I mean, what if you want, P at T equals 0, like at the beginning, but then you want Q at T equals 5. Well, then you're going to have to adjust this R of T, right? And what can you do? Can you come up with a way to adjust this so that when T is 0, you get P, and that T equals 5, you get W? What you can do is you can you can replace t by t over 5. So if you do 1 minus t over 5 like this, v plus t over 5w, now when you plug in t equals 5, you're going to get w, and when you plug in t equals 0, you get v. Okay, so you can always modify the equation of the line. Now notice that this is actually the same line. Like if you have this, and this, these are the same line. When you plug in all the values of t, you're going to get this same line through P and Q. It's just that you're changing which values of t will make you end up at which points. But if you imagine plugging all the values of t, every real number, you're going to get the same line. Okay, so a line can be parameterized. It can be given this parametric equation in lots of different ways. There's lots of different parametric equations that describe the line. And why is it called a parametric equation? Because we think of t as something that's like varying, and it's giving you all the different points of the line, and when you have something like that, it's called a parameter. You're thinking of t as something that you can kind of vary, but while staying on the line. Okay, so that's some practice with parametric equations. This is something that's important in multivariable calculus, for instance, when you're doing line integrals. But for us, we just want to describe, now that we know how to describe a line between 2 points, we can figure out what happens when you have a linear transformation and you plug in all the points on the line. So let's say that you have a linear transformation from Rn to Rm. Okay, a linear map or linear transformation. Okay, well, all the points on this line through P and Q have this form. So what happens if you plug in any vector that has that form? Well, if you plug in any vector of that form, do you see how this is a linear combination of v and w? I have a constant, my constant's 1 minus t, v, plus another constant, t, times a vector, which is w. And so I can distribute the t across, and so I'm going to get 1 minus t, t of v, plus t of w. Okay, 1 minus little t times capital T of v plus little t times capital T of w. Now what does that look like? Well, so let's say that I had an example R2. Let's say that I'm going from R2 to R3. Okay. And let's say that's V, and let's say that's W. So I have this line through these 2 points, and let's say this point is P, and let's say that point is Q. So P and Q are going to be sent by this linear transformation. Okay, T is going to take R2 to R3, and it's going to take P somewhere. It's going to take P maybe to P prime. Who knows, maybe it's here. And it's going to take the point Q somewhere else, let's say over here, Q prime. Actually, let me write the Q prime maybe here. Okay. So what does that give me? My V is my vector from O to P. So here's the origin. Okay. Here's the origin in R3. This O is the origin in R3, the purple O. So V is OP, the vector OP, and W is the vector OQ. Now what's T of V? Well, T of V is the vector from the origin to P prime. right? Because this vector, v, is going to some other vector, and I'm letting p prime be the image of p. So that vector is my t of v. And similarly, the vector from the origin to q prime, that's my t of w. So my t of v is O p prime, my t of w is O q prime. And so what is this? That, do you recognize? It's the line through p prime and q prime. So what this is saying is, okay, so the thing I'm plugging in, okay, this is a typical point on the line through P and Q. And what I'm getting out is a typical point on the line through P prime and Q prime. So what's going on is this blue line is going to this purple line. That's the result of plugging in all the points on this blue line into my function t. Okay, so that's if so this blue line goes to the line. So t maps a line to the line, let's see, I should say it maps the line through P and Q. What's the notation for the line through P and Q? LPQ to the line LP prime Q prime, where P prime is the image of P and Q prime is the image of Q, as long as P prime is not equal to Q prime. If P prime is equal to Q prime, then you just have a point, right? You don't have a line. So let's take a look at that. So suppose that, so if P prime was equal to Q prime, okay, so i.e. if P and Q go to the same point under the linear transformation T, then what's going to happen? Well, in this case, you have a picture like, so here's P and here's Q, and you have this line through P and Q, this line through P and Q, and if P and Q both go to P prime, okay, what's going to happen to the whole line? Well, if you think about it, this output, okay, this output is going to be 1 minus t of v plus t, capital T of w. Now, if t of v is equal to t of w, then this is just going to equal, then this is just going to equal 1 minus t of v plus t, capital T of v, and that's just going to equal capital T of v. So what did we learn? We learned that if P and Q go to the same point under the map T, then this whole line through P and Q is also going to go to that same point. It's just going to go to the vector T of v. Okay? And so what we discovered is that in general, a linear transformation, so linear transformations, they map a line to either a line or to a single point, depending on your transformation. Okay. So let's just look at an example. Let's say that you have the linear transformation given by matrix multiplication where the matrix A is this matrix. The first column is 1, 2, and the second column is 3, 6. Okay, we can visualize what A is going to do. So first of all, the inputs and outputs, the domain is R2, and the codomain is also R2, right? Because A is a 2 by 2 matrix. So let's look at where the vector E1, which is 1, 0, goes, and let's look at where the vector E2, which is 0, 1. Well, we've seen that when you multiply A by E1, you just get the first column. So you know that it's going to, A times E1 is going to equal 1, 2. So it's like this. Okay? A times E1 is going to be 1, 2. And I know that if I multiply A by E2, I'm going to get the second column. So I'm going to get 3, 6. Well, that's actually just the scalar multiple of 1, 2, right? It's just 3 times 1, 2. So A times E2 is going to be 3, 6. And so what's happening is that all of R2, if I take a random point on R2, like this point, okay, if I take like this vector, AB, it's going to get sent. So AB is going to go to, so this is a symbol with the little line with the arrow, that means it maps to. It will go to A times 1, 2 plus B times 3, 6. Which is actually a scalar multiple, 3A plus B, of the vector 1, 2. Right? So every vector on R2 will go to a scalar multiple of 1, 2. So you're going to get this line through the origin as the output. So this line through 1, 2, that's the image of the function T sub A. The mapping that's defined by A. Okay, so if you plug in any vector in R2, okay, all those vectors, they're all going to go to this line. You're not going to get any vector that's out here or anything like that. Like this vector is not in the image. It's not in the image of T sub A. Okay. So this if you plug in any line, you're also just going to get this line as the output. Okay. Actually, this is really an example of mapping the plane to a line. So this maps the plane R2 to a line. Let's do an example where it takes a line to a single point. For instance, let's say that you have the matrix A, which is now, does this take a line to a single point? Let's see. Oh yeah, no, let's look at this example more. Sorry. Let's continue with this example. Can you come up with a vector that will go to the origin besides 0, 0, this matrix? So let's just write this down. So A will send 1, 0 to 1, 2, and it will send 0, 1 to 3, 6. Now can you use that to come up with a vector that will go to 0, 0? Yes, right? 3, if you take 3 times this input, so that's 3, 0, 3, 0 will also go to 3, 6. So you have these two vectors, 3, 0 and 0, 1, that go to 3, 6. Therefore, when you subtract them, it must go to 0, 0. So if you do 3, 0 minus 0, 1, you get 3, negative 1. So this vector has to go to 0, 0. Should I just write that down? So A times 3, 0, by the linearity of matrix multiplication, this is A times 3 times the vector 1, 0. By the linearity of matrix multiplication, this is 3 times A of 1, 0, which is 3 times 1, 2, which is 3, 6. Okay. And we know that A of 3, negative 1, that's going to be A of 3, 0 minus 0, 1, and then by the linearity again, this is going to be A times 3, 0 minus A times 0, 1, and you're going to get 3, 6 minus 3, 6, so that's 0, 0. So A is going to send this line through the vector. It's going to send the vector 3, negative 1 to 0, 0. Technically, it's T sub A. Right? I'm using a different name for the map because, a matrix, A is a matrix, and a matrix is just a bunch of numbers in a box. So I'm using T sub A for the actual function, the mapping. This map is going to send this vector 3, negative 1 to 0, 0. And so what is it going to do to to any scalar multiple of this vector? Any scalar multiple of this vector, okay, any scalar multiple of this vector is also going to go to the origin. So it's going to take this line to a single point. Now what happens if you take a line that's parallel to this line. So let's say I take this green line that's parallel. Okay. Let's say it's, let's say this vector here is 0, 2. So then I can describe this green line as 0, 2 plus any scalar multiple of 3, negative 1. Where is this line going to go? Well, this line is going to go, when I do a times it, a times any point on this line is going to be a times 0, 2 plus, by the linearity, t times a times 3, negative 1. But I know that a times 3, negative 1 is the 0 vector, and so I'm just going to get a times 0, 2, which is the vector 6, 12. So this entire green line is going to go to the vector 6, 12, which is somewhere on here. Okay? So this is an example of a line in the domain, in some sense, collapsing to a point. All the vectors on this line, all these vectors from the origin out to the line, A is going to map all of these vectors to the single vector 6, 12. Okay, so that's lines. That's where linear transformations map lines. They will map lines to lines or to a single point. Now what about planes? So what about the images of planes under linear transformations, under a linear transformation? Well, planes can be described as, let's say you have a plane through the origin first. If you have a plane through the origin, it's going to be the span. So here's R3. Let's say that you have a plane through the origin. Okay, you have two vectors, v and w. Then the plane that contains v and w is this plane like this. I mean, it goes out in infinite directions, but this plane is the span of v and w. Right? It's all linear combinations of v and w. And so this can be described as the set of vectors x, y, such that x and y are some scalar multiple of v plus a scalar multiple of w. So it's of the form sv plus dw, where s and t are real numbers. So this colon means satisfying s and t are elements of the real number system. And so if I have, so that's if I have a plane through the origin. Now if I have a vector that is not along the origin, so if I have a vector A, so I have this vector A, I can translate this entire plane along the vector A just by taking all the vectors on this plane and then adding the vector A. And when I do that, I get this translation of this plane by the vector A. So this this plane, if I write it A plus SV plus TW, okay, so my original plane down here goes through the origin. And when you add A to all the vectors on the plane, you end up just translating all the vectors on this plane to this other plane. So that's this plane. So let's write that down. So this plane, I don't know, let's call it curly P. This plane it's all vectors, how do I write this? And this is in R3, so it really should be X, Y, Z. It's all vectors of the form A plus SV plus TW, where S and T are in R, are real numbers. So that's how you would describe this plane. So if I call this original plane Q, this P is the translate, it's called the translate of plane Q by the vector A. So plane P is the translate of plane Q by the vector A. Okay. So now that we have that understanding, okay, now let's look at what happens when you apply a linear transformation to it. So let's just look at a concrete example. Let's say that you have a plane which is given by 1, 2, 0 plus S 1, 1, 1 plus T 0, 1, 1. Okay. So this is going to be a plane, and it doesn't go through the origin. Okay, because this vector 1, 2, 0 is not on this plane. So if I just didn't have this, okay, if I didn't have this, this would be a plane for the origin. But since I have it, I have this 1, 2, 0, what's happening is I have this plane for the origin, and it's being shifted. All the vectors are being shifted by that vector, and so I get a vector that doesn't go to the origin. Now when I apply a linear transformation T to it, so I get this plane. What happens if I take a typical point on the plane and then plug it into my function capital T? Well, by the linearity of capital T, I'm going to get T of 1, 2, 0 plus S times T of 1, 1, 1 plus T times, plus little t times capital T of 0, 1, 1. And now I have, what does this look like? So I have this vector T of 1, 1, 1, T of 0, 1, 1. Okay, and I have this vector here. This is the form of a plane. As long as, so this is a plane, as long as T of 1, 1, 1 is not a scalar multiple of T of 0, 1, 1. So in other words, you need these two vectors to be linearly independent. yeah, maybe it's better, it's more accurate to say if these are linearly independent. So, because, you know, you can have one of these vectors be the zero vector and then another vector is not the zero vector. So it's a plane as long as the set T of 1, 1, 1 and T of 0, 1, 1 is linearly independent. Okay, because so what's going to happen is I have this plane that doesn't go through the origin in my domain, and what's going to happen to it is if I have, so I have, let's say that I have a linear transformation from R3 to R3. So if T of 1, 1, 1 is like here, and my T of 0, 1, 1 is, let's say, there, okay, then I have this plane that goes through these two vectors. This plane goes through the origin. So if I didn't have this, right, then I just get this plane through the origin. But now I have this T of 1, 2, 0, and so that is going to shift this plane by T of 1, 2, 0. So if I have, you know, let's say that's my vector T of 1, 2, 0, then what I'm going to get is this plane that's shifted by T of 1, 2, 0. So this plane that doesn't go through the origin is going to go to this plane. What happens if this set T of V, T of W is linearly dependent? Okay, and at least one of these is non-zero. Well, that means that one of these vectors is a scalar multiple of the other. So let's say that T of W is some scalar multiple C times T of V. Well, what I'm going to get is T of 1, 2, 0 plus, you know, S times T of V plus T times capital T of W, but then capital T of W is C times T of V. And so this is going to be T of 1, 2, 0 plus, now here I have some scalar multiple of T of V. It's S plus TC times T of capital V. Now what does this look like? Do I have a line? No, I have a, sorry, do I have a plane? No, I have a line, right? This is going to be a line. What it's going to look like is I have T of 1, 2, 0. Okay, that's going to be some vector. I don't know, like maybe here. And then I have this line that's parallel to, okay, I don't want to make it look like it's perpendicular. Okay, I'm going to get this line that's parallel to T of V. So if T of V and T of W are linearly dependent, then this plane is going to get mapped to this line. And then the extreme case is if T of V equals the 0 vector and t of w is the 0 vector, well then my output, which is t of, what was it? 1, 2, 0 plus s t of v plus t capital T of w. I should have clarified that I'm calling this vector v and I'm calling this vector 1, 1, 1 v and I'm calling this vector w. Okay, that's v, that's w. If t of v and t of w are both a 0 vector, then I'm just going to get that this is equal to t of 1, 2, 0. And so when I plug in all the vectors on the plane, I'm just going to get a point. I'm going to get a single vector t of 1, 2, 0. So to summarize, if I have a plane and I apply a linear transformation to it, there's 3 possibilities. I could get a plane, I could get a line, or I could get a point. Okay? So hopefully that gives you an idea of how linear transformations behave. It would be a good idea to play around with some concrete examples with a specific matrix to see what happens. And in the next video, we're going to talk about how to find the matrix of a linear transformation. So if you have a linear transformation from Rn to Rm, it has an associated matrix, and we're going to learn how to find what that is. Okay, thanks for watching.